the title of my talk is from Crete to Cloud, from Edge to whatever. So as you can see, I don't think that we're actually right now at a stage in edge computing where we reach the solid abstractions and bulletproof services that industry offers us when it comes to cloud computing. And so I want to reflect a bit backwards on where we came from. Let's just start to see what people typically research and using when they're talking about edge for whatever computing. They're talking about a continuum of computation that happens on whatever nodes out there. And if you Google computing continuum, then this is pretty much what you will get as picture. So you don't have to see it there, but it's always starts somewhere in the cloud, reaches out to smaller devices that typically sensors provide information, pumping this somewhere into. Sometimes there's some interaction between the devices in between, and so the question is, are we there yet? Who thinks we are there yet? Building by somebody, you can build systems by edge computing, things by the Lenovo, by other vendors, system-wide stuff. So hardware-wise, there's a lot of things there which claims to provide something like edge computing. On the software side, it's starting, okay, doing Kubernetes stuff, and I want to end up at the end and just say, but still there are open issues. And if you take just some kind of time travel and look at what computing was before. In the old days, typically we had less computing power than demand. So you put your punch cards in, you had an error in your compilation, were frustrated. So typically people waited for a computer. This changed a bit with things becoming more and more decentralized. It's not necessarily that your program is better, but the response is going kind of faster. And if you're looking at the time being, and most of you know this picture from Weiser's seminal paper about the computer of the 21st century. Somewhere in the 80s we had a one-to-one relation of processors to people or persons, and these days we have processors everywhere. The small device, maybe in the microphone, in your cars are 30, 40, even more processors, Astros, who knows better how many processors are deployed these days in modern cars. Our coffee machine, this was the initial version we had in our crew, had actually 3 processors in there for the brewing, for the control, and for the front panel. So processors are obviously ubiquitous, and by that, all of a sudden we had excess capacity. And there was a lot of work starting and priming the field for grid computing. So starting with Condor and Utka's work about finding island workstations and trying to offload or share work somewhere onto that. And then there was a lot of ubiquitous computing, mobile computing stuff, fostered with grid computing as the big abstraction, and all of a sudden we have things here. So let's reflect shortly and briefly about the success of grid computing. Is there any services around these days for grid computing? So has anybody of you used grid computing recently, the last week, month, year?
Maybe we as a wrong crowd, right? We should talk to American analysts, physicists, and so on.
Well,
they call it cloud now.
No, fundamentally different. Who's the, to your knowledge, do you know anybody providing grid services? The only institutions I'm aware of who are providing grid services are university computing centers in Germany, and they charge you for your own resources, which is completely crap. And this is why even in Germany, the universities using the university computing centers' resources wouldn't use it. So I guess Crete was a nice idea. There was Boeing had some reach, but pretty much everything is kind of dead in this domain, at least my view. And if you're reconsidering how many cloud resources you use in the last days or hours, pretty much all our things sync into the cloud, are connected to the cloud. So obviously there is something which pretty much holds the promises that grid computing had, and grid computing didn't. And so why is that so? Obviously both are aiming at the same goal, providing some kind of elasticity, using resources, combining them in a way that are easily to achieve and manageable by the user. If we're looking at control operation, centralized, decentralized one, Crete aims at the integration of decentralized resources in a centralized coordination, and cloud resources, they are centralized. It's many computers, but many computers with strict governance, typically in a physically enclosed space, say a data center. It's the same computers, you have the governance about the hardware, the software, everything. So you don't take any credit stuff from, you know, last year's grant and combine it with next year's grant, hoping that it somehow will work. And because it's only scientists, you don't care about your customers. This is a fundamental difference in what you're offering and how you're offering and making it operational. And this is one of the key things. Next thing is homogeneous versus heterogeneous. The heterogeneity of cloud environments pretty much kills you. And with the service model, that comes easy if you're homogeneous, that you can virtualize versus running tasks. So if you're desperate, you're running something like, oh, let's take Java and have virtual machines and deploy things like that, that somehow cope a bit with the heterogeneity, like grid computing people do. The success of cloud computing is here's your virtual machine. And then you charge it by the hour, by whatever things, but this is an abstraction that is simple and it works, and it only works because you're on the same homogeneous platform in a controlled, centralized environment, which is somehow distributedly available or input from the outside. But actually what we're doing is we're buying a data center with, or we're running a data center without knowing how to do this. And this is fantastic. And obviously grid computing really does not do this in a nice way. Now, how does this bring us to edge computing and where we are at that point? So what's missing there? So when it comes to the cloud, we pretty much know how to do it. Well, I don't pretty much know how to do it, but I know that there are tools, there are vendors, things I can go buy, nearly close to, you know, click and play, no code deployment and stuff, and things just out of a sudden scale and work nicely. This is cool. Next thing, if you're looking at the edge, I mean, there has been 30 years of research in mobile computing, ubiquitous computing, home automation, all that stuff. There have been, I think, less profound standards and less single rollouts of, you know, technology and tool chains as we have seen or we can see in the cloud computing. But still, there's a lot of standards. There are operating systems out there. There are things like Genies. I always use Genie as an example for software archaeology. So Genie gets reinvented every 2 or 3 years, and in a worse way than it was actually deployed initially. And this was printed by Sun. It was shipped with HP printers, and it was fantastic. So if you want to have something that dynamically orchestrates your thing, use Genie, or if you're desperate, OCI extend. Typically, what we're having here is something like more dynamic deployment, locally, local governance, less security issues handled, less things like application model supported. So it's a rather unstructured thing, more and more of how applications look at that. And if you look at what industry looks at this is just sensors. So when it comes to the continuum view, these are just data sources that provide things at the edge, should somehow be controlled, aggregated, reduce the load into the network, but less considered to be supported by services or even used or doing things in between. So this is typically either still research things or what people are just doing if they like to hack or code or obtain PhD thesis, which typically is often pretty much the same thing. So the question is, what is somewhere here in the middle, what helps us just to glue the whole things together, or does it at all make sense to do so? Well, I guess still, as long as people are talking about this continuum thing, there is something in there. So the question now is, how can we provide computation services from cloud to mobile, mobile to cloud? So in both ways, we had some discussions in the instructional seminar that there are those two kinds of application scenarios here. You can look at the thing from a mobile computing perspective, saying, I'm moving there, I want to have my services as I roll through the environment there. The other thing is, I want just to catch the data from the sensor into my cloud-based application. And obviously, all those devices are still things to interoperate, cooperate, for whatever reason, on a spontaneous network way. And so, how can we try just to put these things together, work with the different error models that are there? So sometimes, especially if you're thinking about mobile devices, being not available does not mean that something bad has happened. It just means that you're temporarily not available, like, you know, with the phone service we call later. In the old days, with land-based phones, if a phone line didn't come, you know, there was an error. In mobile phones, you just not connected, running out of battery, out of reach of the network. And how to integrate this in some kind of a uniform abstraction or middleware platform is still a question. So we have something heterogeneous. We found out heterogeneity was what killed grid computing. It's decentralized. This was also a problem with the grid computing stuff. And we decentralized the governance and the control, and we have a lot of dynamism in there. So it's even worse than the situation grid computing had, what I still claim was kind of a nice idea, but still a failure. Any good idea or solution to that? This is the question. I think it's worth thinking about what's the right abstraction in order to make these things working and becoming part of an application architecture. And so what I think, if you're looking locally, we have threads or processes which just spawn, run, click. For whatever remote, we have typically kind of services in there. We can upload it, ship the services, we can ship the services as a closure, then we call it serverless, but at the very end it's just some kind of code that is executed service. In the infrastructure, we typically deploy virtual machines. And now how does this decentralized and a homogeneous abstraction from the claim that this was what cloud computing made possible or so desirable look like here, or can we achieve this? And this is the part where I typically would talk in length about 12 years experiences of edge computing platforms in different stages. Guido remembers one of the first talks I gave in an interview at Bamberg, in an interview schedule, and it said, we don't know yet what to do with that, but it's a nice idea. And then we found out edge computing is actually one of the applications of a framework we reworked over the years. And I guess for time saving, I just give this a bit, or give you at least a few glances about how we started. Go to the end of the talk and hope that we will have enough time over coffee and because to catch up on the in-between parts. So this started in 2010 when actually the first deployment of Amazon cloud system came up, and if you look at this cloud computing stuff and the Google App Engine pretty much at the same time, to find out that in the one point you had a fine granular metering by number of requests, but you had applications that had to look like web services. So they would process HTTP requests. It's just not really a generic application architecture. EC Cloud was very nice. You already start deploying virtual machines, but you were charged by the hour. So when you were done after 45 minutes, Amazon was happy. Later they introduced the spot market for the residual times in that, but at that time this was the early environments, and we just thought at that time, what could we do or play something in between? And the idea was, I was in my sabbatical, and Steve Boyce's group, and Justin, one of his PhD students, just finished his thesis, and he developed a platform with a small virtual machine, and the core idea was just to ship some code for marshalling. So we had some kind of a high-level interoperability framework. And this was small and nice, and the core idea in a nutshell was deploying this interpreter as an idle process and then doing some kind of tit-for-tat sharing. And well, it's obvious what to do with that. And so a bit like say at home, if you think, oh, this looks like a file system in inodes. Yes, this looks like a file system in inodes. So this is the core idea of Justice architecture. He introduced something like chunks, pretty much everything where was junk, with the chunks you could model things like stats, a function call, and refer to it. If you need more space, refer to the next jump, just like in inodes. It was an awkward programming model which boiled down to some kind of JavaScript stuff, but still it was not really nice to do it, but what we could do with it, and this was one of the basic abstractions we observed at that time, and still find it nicely and see this reflected also in today's vision of serverless computing. We have closures as our fundamental processing model. So data comes with a code, you send it somewhere, and it gets interpreted by this rather awkward architecture or runtime system we just borrowed because just developed it for just another reason. We had a simple trading service, kind of centralized picture, and then we started playing around with it, and one of the core things we liked was that it reflected a bit of best effort semantics, so a bit like, you know, IP or data trends if you're looking at transport data in UDP. So if you had a computation that wouldn't work, that could have been for various reasons. So for instance, you sent it to an EC2 instance that was just about to die because it was finished and done. So sending the request to the same instance again wouldn't help because it wasn't there. If you're just out of connectivity, coming back to connectivity and resend things, that does not make sense. So different reasons for error require obviously different mechanisms to work with that. And doing a separation between things like policies and the mechanisms to cope with that came into play, and then we thought about do something like thinking about best effort containers. They are a casted container, so running these small closures is something like computation as a best effort semantic. And all the computation before we think of was not necessarily best effort. If you give a task or schedule a task at the operating system in some remote service, you expect it to eventually finish, right? And depending on the scheduling discipline, it will do so. And this is fundamentally different here. And with that, we played around, and it's a bit like the inverse Christian. So you have this small tail, like in IP, and then you have all the services on layer 4 above and all the technologies below. And so this was kind of the picture that we had. And then we started building from those tasks at 1.0 into various or further versions of tasks. And this is the part, unfortunately, I have to skip. It was a lot of PhD theses. We won best paper awards, so things to brag about. So if you want to see me bragging, ask me about taskers. We realized the platform. We worked on decentralized context-aware scheduling. We used this for offloading. We looked at energy-aware offloading. So a lot of things. And who of you has ever heard of taskers? Ha, at least. Who of you has ever thought of using taskers?
Right now.
We are equal with the mythos, the upgrade was. So, this is kind of the doom of a question of volunteering for using taskers.
I think last time we were talking about tasklets.
I always talk about taskers.
Last time I asked you how are the different cloudlets, and you didn't tell me. And you not tell me.
Just another platform with the combination, and I'm coming back to that. So obviously we didn't manage to take over the world, at least when it comes to edge computing and something like mobile stuff. Maybe I should have written Montgomery's book before. Anyway, nobody obviously is really into taskers except of us, and we are still rethinking how much we are actually in this task business any longer. So if you're looking at it, it's a stable platform. It's for 4 PhD theses, a number of master theses. We have calibrated the stuff, we built it into Omnet, we did experiment with zillion of, well, a lot of computers, we scaled it out by that. So this is really something which works as a scientific engine, and it's platform enough to do real world deployments. But we use an intermediate language we call C-. It's not really a good language. We had our own platform, which is a small stack machine like in PL0 in early versions, or you see C Pascal of P system, which was not a very good runtime. So the closure is actually a pretty nice concept, but if you're thinking about stuff like pictures or MapReduce stuff where you have a lot of data, a little of code, wrapping this in closures and sending it around between edge devices is close to idiocy. So closures are nice, pure and clean, but not necessarily good in all occasions. So
that's the business model of streaming services, Akamai, content distribution network. That's what they do, right? Because if you are, if you want to see a movie that your neighbor is seeing, it's stupid to move around terabytes of data just from A to B twice.
That's the multicast problematic. Happy to talk about that later. But here's just the reflection about our service model. And so, plus our point, there are other platforms, a lot of good platforms around, since the people love to use Go these days, so pretty much everything at the edge turns to run into some kind of Go-based platform. So at the edge we have these different application modes we talked before. So we have cloud-based stuff, thinking we want to integrate sensor data. We have this mobile computing thing, so walking around and just looking for some services that hopefully with some kind of handover mechanisms follow me, like in all the old mobile computing, ubiquitous computing vision papers, and obviously some kind of a hybrid thing where things might connect somehow in between. And for the runtimes, there is a zoo of different stuff. There are different involved parties, which makes it actually pretty interesting and also seeing the governance. So from a perspective where you can make money of, the last thing which makes some sense is hosting obviously some kind of a small cloud at the access network. So it'll, I don't know if they already made the deal, so when Google was trying to take over Verizon, then out of a sudden we have the situation where somebody providing cloud services then also provides the access network and then is able to put the data centers there and providing that part of the continuum as a service to customers. And so far, to the best of my knowledge, nobody else actually could do something like that. Maybe the telecom, but I guess they're kind of agnostic to business models. Anyway, there's some things I think we learned, so doing too much or trying to do too much homogeneity by virtual machines and stuff ignores a bit the characteristics of the different devices. So you need to cater for some of the heterogeneity there, and also there's so much of good platforms around, just saying stick to one wouldn't really make too much sense in that area. We need to support something decentralized control coordination. There is a lot of locality already in there, which also fits into the big picture of, say, the cloud-based applications, where you try to aggregate the data where it stems from, take the combination at a reduced flow rate, and put this into the cloud in there. From the mobile computing perspective, obviously roaming through the world and handing over from access network point to the other one, warming up the caches, having the data, the models, if you're doing something like, say, prediction models somewhere running these edge-based will be necessary. And obviously, one of the big lessons learned in the internet, if you don't offer a service, if you charge and bill it by quality, you cannot differentiate the quality. So you need to have something like a business model and billing model at the very front when you're starting deploying such a platform. Otherwise, you just run best effort services without any differentiation. And so, still have 1 or 2 minutes left. This big picture, but I think this is the next thing of where we as a community might think of. You have something where you have those local areas, say access networks, you have nodes running through, meeting each other, exchanging, roaming, and in the big spot, something like access to, the big cloud backbone. So think of kind of a hierarchy which is graphically represented here. So we need cater for heterogeneity, decentralization, roaming, and quality of billing. And what is the core thing here is that we need something like services in order to glue the thing together. So thinking about, I'm a systems person. I love to build things, I love to see my people build things, I love when it blinks and honks, both at the same time, it's even more better. But at the very end, you need some architecture, a glue that brings the whole thing together. And the one thing you can learn actually from the internet is the internet says, thinking protocols, not architectures. Even though this might be frustrating for systems people, well, you can be a systems person working on protocols as well. So, and showing that architecture that it works. But this is, to me, the thing we need to talk about and we should do when it comes to cater for the variety of resources we have there. Just in the same way that we exchange taskers, cloudlets, whatever, every proprietary platform ships through the world. You can then say, I want to have a resource for computation. I have code for, say, WebAssembly and a cloudlet and maybe old-fashioned taskers, and then the trader can offer me the same thing with some kind of quality of service description or some service level agreement, possibly, plus also with some kind of price tag. Whether this is a real currency, this is a crypto, or whether this is just a tit-for-tat share, while I reciprocally offer some of my resources, doesn't matter, but we need to have something like, some tin cans, whatever stuff, or marbles in order to do some exchange. Now, the question is, why should we do this? Actually, let's talk, and I'm pretty much at the end of this talk, so hope to catch up with you in the future. Thank you.
Guido, maybe two comments. The first one is, you talked about mobile cloud. You completely left out everything that is stationary.
Another word for, you know.
But you have sensors, you have a lot of stationary things, and they are spread. Think about something, disaster recovery also. That's one only comment. And the other is this second last slide. This was the product, yeah, this one. No, the last one. It's just, okay. I teach a lot about SOA and web services. And when you start with the starting slides from 201, 203, you have exactly this, and with the protocols, everything has gone down the drain. Because your protocol suite, that is a stack of things nobody wants to standardize, and you lose at the very beginning with this approach, I think, because we've seen it in the last 20 years or so.
Well, but SOA started with complicated, slow protocols where more efficient protocols were existing. And even these days, people are using JSON and they're wondering why things are slow. So think about session initiation protocol, other stuff which is in the, this is, you know all the standards. So core services that work. The question is, I don't know whether this will work, frankly. And if you ask me after 3 meters, I'd say a 90% that it doesn't, maybe 95. But the question is it worth the effort? Otherwise, what we will receive is having a centralized business case or just some kind of extended cloud, and we get what they will offer us. And the question is, if we, grassroots-based, could offer at least, thinking of IPVS standards, something coming upwards at least a bit, and making sure that there are at least protocols available that might be adopted in order to provide us to integrate this stuff. Might be wrong, I think.
There are protocols, and all these, for example, low-level messaging protocols nowadays, and so on, they really work.
Sure.
You can easily adapt them to the cloud or the edge of the cloud.
But you need the portfolio. So when the SOA people started interoperating using XML, there was IOP around there, which did work with the 2% overhead of a raw TCP, a very efficient protocol, completely ignored.
So the problem was that some companies didn't want to use it.
Yeah.
Microsoft was against it, so we need to invent something new.
Well, but Microsoft actually provided a very nice architecture by switching it to a native protocol that's fast, or using something slow for, accommodating all the others, which is then.
So SOA was the business case. It was not a technological stack. It was all about business.
But I guess this is exactly the point where we have all the technology. Is it worth it or not? But right now I'm going into the next session's time. So I'm here, I'm happy to talk about that. Punch me and see what happens. Holger?
Yeah.
Ich mach's wieder an.
So what?